In this section, we're going to look at graphing quadratic functions. This is going to be a rather long section. There's definitely going to be multiple videos. There are two different forms of quadratic functions that they're typically written in. One is called standard form, also known as vertex form. We're going to take a look at this one first, and we'll see why this is called vertex form. And then after we can finish vertex form, we'll take a look at quadratic functions written in something called general form, whatever that is. Well, let's say I asked you to graph y equals x squared, and you knew absolutely nothing about y equals x squared. The most reasonable thing you would do is build yourself a table. So that's what I'm going to do. If I plug in -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. So I have -3, 9, -2, 4, -1, -1, 0, 0, 1, 1, 2, 4, and 3, 9. The first thing you absolutely need to notice is you do not get a line. And you shouldn't expect to get a line because lines have just an x, they don't have an x squared. You get what we call a parabola. That kind of shape. Now, on a parabola, there are some very important things. The first is this point right here. This point is called the vertex. So a parabola, and for us, is either going to be something that looks like a big U, in which case the vertex will be the lowest spot. And in a few minutes, we'll see that sometimes you get an upside down parabola, and then the vertex will be the highest spot. So that's known as the vertex, that point right there, the lowest spot. And then we also have something that we call the axis of symmetry, which in this case is x equals 0. It's the vertical line that goes right through the vertex. And it's called the axis of symmetry because what happens is if I could take my piece of paper and fold it right along this line, this side of the graph would match up perfectly with that side of the graph. And so this is called the line, sometimes called the axis of symmetry. I prefer line of symmetry because it's not always on an axis. In this case, it happens to be right on the y-axis, but it's not always on an axis. So you'll see it called both things. The other thing I want to point out is notice the symmetry here. We had, if I went one step from the vertex, my y value was 1. If I went one step from the vertex on this side, my y value was 1. If I went to x equals 2, y equals -4. So if I went, or y equals +4. If I went 2 steps to the right, I got y as 4. If I went 2 steps to the left, I still got y as 4. And you see that in these numbers, that you see repeats in all the numbers. So finding points on a parabola is going to get easier once we have an idea of where the vertex is. If I have the points on the right-hand side of the vertex, I can just use the mirror property and I immediately get the points on the left-hand side of the vertex. Alright, let's take a look at this one. What happens if I have y equals x squared and I do a -3? Well, let's see, if I plug in, -3 squared would be 9. 9 minus 3 would be 6. -2 squared is 4. 4 minus 3 is 1. -1 squared is 1. 1 minus 3 is -2. 0 squared is 0. 0 minus 3 is -3. 1 minus 3 is -2 again. 4 minus 3 is 1 again. And without doing the work, I bet you're convinced that that last one is 6. You see the repeat in the numbers. Alright, plotting that out. -3, 6. -2, 1. -1, -2. 0, -3. 1, -3. 2, 1. And 3, 6. So what changed between y equals x squared and y equals x squared minus 3? Well, if you look all of the y values are exactly 3 smaller. 9 minus 3 is 6. 4 minus 3 is 1. 1 minus 3 is negative 2. So what happened is we took this picture here and we simply slid it down exactly 3 units. That's what that minus 3 did right there. Slid it down exactly 3 units. So our vertex now is the point 0, negative 3. The negative 3 simply moved the vertex and moved the whole rest of the graph. And our line of symmetry hasn't changed. It's still x equals 0. Okay, let's take a look at y equals x squared plus 1. And you probably have a good idea of what's going to happen here, but let's work it out just to make sure. 9 plus 1 is 10. 4 plus 1 is 5. Plug in negative 1. 1 plus 1 is 2. 0 plus 1 is 1. 1 plus 1 is 2. Plug in 2. 4 plus 1 is 5. And then you get 10. So we have negative 3, 10. Negative 2, 5. Negative 1, 2. 0, 1. 1, 2. 2, 5. And 3, 10. And so, oops, I missed a dot there. Ooh, boy. Bad dots. Make your dots bigger. Shouldn't be a little hoop-de-doop there. Ignore that part. It should be a nice, smooth curve. Anyway, our vertex is 0, 1. So, I was guessing you wouldn't be surprised. The plus 1 did the opposite of the minus 3. The minus 3 moved the graph down by 3. The plus 1 moved it up 1. Now, I could have built a bunch of tables and shown this to you, but I thought it was quicker to just have a computer draw it and show you that. Let's say I had x squared. X squared is the black graph here. And then I did x plus 2, and I put it inside parentheses, and I squared it. The natural instinct would be that what's going to happen is the plus 2 is going to shift it to the right 2. But we can see what happened in the graph is the plus 2 really shifted the whole parabola left 2. So our vertex on this one became negative 2, 0. And think about why that happens. I am going to build a little bit of a table. If I build a table, I'll plug in these numbers. If I plug in negative 2, I'm going to start there. Negative 2 plus 2 gives me 0, and 0 squared is 0. And that's going to be the lowest spot. The reason that's going to be the lowest spot is because when I plug any of these other numbers in, I'm not going to get 0 here. So when I square it, I'm going to get a positive number. That makes sense? Let's plug a few of these in. When I plug in negative 3 plus 2 is negative 1. Negative 1 squared is 1. When I plug in negative 1 plus 2 is 1. 1 squared is still 1. Plug in 0, I get 2 squared, which is 4. Plug in negative 4, I get negative 2 squared, which is 4. So do you see, when I plug in negative 2, I get 0, which is going to give me my lowest spot, because anything else squared is going to be a positive number. So it's kind of like you would have to subtract 2 on both sides, if I had x plus 2 equals 0, to figure out where is x going to give me the 0, which is going to be the lowest spot. Alright, so the whole key to remember here is this. When I put numbers outside of parentheses, like this negative 3 and this positive 1, oh, you can't see the positive 1 that I just circled. There it is. This negative 3 and this positive 1, it moved the graph up and down. And it moved it the way you think it should move it. A negative 3 moved it down. A positive 1 moved it up. When I put numbers inside the parentheses like so, it's going to move the graph left and right, and it moves it the opposite of your instinct. A plus 2 in here moves the graph to the left. Conversely, I have a picture here to show you. If I have a minus 3 in here, it moves the graph to the right. Here's my original y equals x squared. X minus 3 quantity squared is here, and notice how it shifted it to the right, and notice how the vertex here is 3, 0. So left and right works backward. A minus moves to the right, a plus moves to the left. Alright, now what happens if I put a number out front here? Here's my y equals x squared, it's the black one. And here's my y equals 2x squared. Now, the way most people would describe that is 2x squared is skinnier, which I concede that that's how it looks, but that's not really what's happening. And I'm going to build just a little bit of a table again here. I'm going to have x, x squared, and 2x squared. If I plug 0 in, I get 0 for all of them. Nothing changes there. If I plug 1 in, 1 squared is 1, 2 times 1 is 2. If I plug 2 in, 2 squared is 4, 2 squared is 4, 4 times 2 is 8. So what's really happening here is when I plug in 0, the y numbers are exactly the same because 0 times 2 is still 0. When I plug in different numbers, whatever number I get here, I get twice as much there because I'm multiplying by 2. So what's happening really is to go from the black graph to the red graph, really what we're doing is we're grabbing the ends of the black graph and stretching it up. So this is called a vertical stretch. You're really sliding the graph, pulling the graph up, except the vertex doesn't change, the vertex stays fixed, and you're stretching it upward. You're not really squeezing it sideways. And then we have the same thing here. If I use a fraction here, again, it looks like we're making the graph wider. We're not really making the graph wider. What we're really doing is grabbing the black graph and stretching it downward. And again, I could build a little table here real quick to try to demonstrate that. I'm going to plug in some good numbers to use. 0, 3, and 9. I get zeros there. 3 squared is 9. 3 squared is 9. 9 times a third is 3. So you see how that's really being divided by 3. So we have the 3, 9 and the 3, 3. It's really just taking this point and pulling it down to there is what's really happening. It's not really making it wider, it's really making it less tall. 9 squared would be 81. 81 divided by 3 would be 27. So you can't see that, that would be way up high. But again, what we're doing is we're taking the 81 and we're really sliding it, pulling it down to a height of 27. Alright, that's going to end the first video here. And we'll go to the second video and we'll put all of these ideas together.